Okay, so we're going to do this video on binomial expansion. So binomial expansion, obviously one of the new things that we have for fifth year and for leaving cert that we wouldn't have done at junior cert. The general idea of a binomial we've already met. A binomial is a type of expression or polynomial. If we think of that word polynomial, it's a particular type of polynomial that has two terms. So obviously that's kind of the bi part of the word. And the two terms we can kind of think of like a plus b. Okay, so two terms in an expression. So as we've kind of said before, an expression is kind of a math sentence that's separated by operators like plus or minus. So a binomial expansion, we're going to be looking at expanding brackets of the form a plus b to the power of n, to the power of something, where obviously a plus b is our binomial part. To solve these questions, we're going to use our binomial theorem, which is in our log tables. So it's not a theorem that we need to know of, but we're going to talk through kind of what happens when we're applying this theorem, and we may find that it's kind of just easier for us to get a general sense of using that binomial theorem and what happens at each stage rather than kind of relying on the theorem, I suppose. But generally, the theorem is there for us to be used and is in your log tables, so you don't kind of need to know it off, I suppose. When we're looking at this formula, then there are a few things that are kind of new to us, I suppose. So we have obviously our x plus y on this side to the power of n. We can see then that we start off with this symbol here, which just means sum. The capital sigma there just means sum. And we can see here, it's a little hard to see on the screen there, but if you're looking at your log tables or your notes there, we can see that we start with or equals to 0. And that's quite important there. So we start with the value of or being equal to 0, and we work our way up then to or is equal to n. So we're always going to have one more term than the power that we're looking at. And if we think of squaring brackets, and things like that, we generally would end up with three terms. If I had x plus 2 and I squared that whole bracket, I would end up with a quadratic term of x squared plus 4x plus 4. So we end up with three terms even though it was to the power of 2. So it's that same idea coming in this case here as well. We can also see then these n choose 1, n choose 0, n choose 1, n choose 2, this n over a number. And that's a very particular type of operator that we have, okay, and it gives us the coefficients. It's kind of a choice operator. We're going to look at what that exactly means for us, and we're going to be using our calculator primarily to compute those values. Those values actually come from a thing called Pascal's triangle, which I know we did look at a little bit in class as well, and there is obviously more in your book about that. But in terms of kind of practically us using this, we're going to be probably using our calculator mostly to compute those values. So if we just quickly go through some of these notes here, so n is the power given in the question. So applying our theorem, will be given in the question, whatever the value is. This n over or, the n choose or, refers to the number of ways of choosing or objects from n different objects. So for example, if I had, say, 3 objects, and how many different ways could I choose one object from 3 objects? Well, obviously 3 different ways if I was just to pick each of the 3 different ones. If I had 3 objects, how many different ways could I choose 3 objects? Well, then of course it's only one. There's only one way that I could do that. So that's what we're looking at in terms of what this operator means. We're also using this idea of a factorial, which is something we're going to come back to a little bit later. But it's important to note as well that when we're looking at this operator, if we have, say, n choose, so 6 choose 4, that will give me the same value as 6 choose 2. Because for any value, if I have 6 here, 6 take away 4 is the same as 6 choose 4. Okay, and that's what we're just going through here. So say for any number, say it was 9, if I had 9, choose 3. If I was asked to find another value that would give me the same, if I was asked to, for another value, 9, choose something that would give me the same answer, that would be 9, choose 9, take away 3, which is of course 9, choose 6. And we see that again, and we would have seen that when we were doing our Pascal's triangle, we would have seen that the values tend to repeat after a certain kind of middle point. We're going to look at an example here. So we're using the binomial theorem to expand 2x minus 3y all to the power of 5. So the first thing we can do is kind of label our terms here. So in terms of using our formula and using our theorem, we're going to consider this as being kind of A, and we're going to consider this part as being B. and noting that we're taking that negative, that minus sign, in with the b kind of definition there as well. So looking at our theorem then, we're going to be doing to the power of 5. So we're going to be starting with 5 on the top, and we know as well that we always start with 0. We always start by choosing 0 things. So if I start at 5, choose 0, then we have to kind of go back to our theorem and see what comes next. Well, if we look at our theorem, we're looking at this part here. The theorem says x to the power of n, and by x there they just mean that first term. So what we're going to do is we're going to take our first term, which is the 2x, and we're going to do that to the power of 5. Okay, if we're continuing on then, if I was to go next, I would go 5, choose 1. I still have my 2x, and this time it's going to be to the power of 4. So we see that for the first term, the powers are decreasing. So let's just make a note of that. So for the first term, powers decrease. Okay, and again, this might be something to make note of in your notes as well. And for the second term, the powers go in the opposite direction. The powers increase. For the first term, the powers decrease. For the second term, the powers increase. So what that means for us here is we just get minus 3y. Going next then, if we do 5, choose 2, we're going to get 2x to the power of 3, and we're going to get minus 3y squared. We'll keep going, 5, choose 3 then. We're going to get 2x to the power of 2, and I'm going to get minus 3y to the power of 3. And we can keep going then again, 5, choose 4, we have 2 more things, 2x times minus 3y to the power of 4, and then finally 5, choose 5, 2, and the 2x will be gone altogether, and I get minus 3y to the power of 5. So we can kind of see there that for these binomial expansions, the first term should just have one of your 2 terms from your binomial, and the last term then should have the other. If we think about how that kind of comes about, as the powers decrease from 5, say in this example, they go 5, 4, 3, 2, 1, and then lastly we get to the power of 0, and we should remember from our indice rules that anything to the power of 0 is just 1. So in that way we get rid of those values there. Important as well just to note that writing out this line helps us remember that when we're doing the powers and things like that, we're going to be including the coefficients of the x as well. It's very easy to forget those coefficients when you're doing these expansions. So laying it out in this way, though it seems kind of long, is a good way for us just to make sure we remember those. So looking at our calculator then as to how to compute this 5 choose idea, we're going to be pressing our 5, then we're going to be using this button that's above divide here. We can see the NCR. And by pressing shift and pressing that button, I end up with that C in the middle there, and then I can do 5, choose 0. Obviously, now this depends, I suppose, on your calculator. Now we're doing 2x to the power of 5, so let's do 2 to the power of 5, which gives me 32x to the power of 5 in total. Next, we're going to do 5, choose 1, which is 5. I'm going to be doing 2x to the power of 4, so let's do 2 to the power of 4, gives me 16, so 16x to the power of 4, and that's going to be multiplied by minus 3y. Then we go 5, choose 2, and I get, okay, let's just make sure I've cleared that first. 5, choose 2 gives me 10. I'm going to get 2x to the power of 3, so 2 to the power of 3 is, of course, 8. So I get 8x cubed, and minus 3y all squared will give me 9y squared. Then we have 5, choose 3, that gives me 10. 2x squared gives me 4x squared, so 2x all squared gives me 4x squared. And then 3 to the power of 3 gives me 27, and it will be a minus a negative 27 here because we've cubed it. So squared obviously makes it positive, but we multiply again then by a negative value, so that gives me a negative value overall. 5, choose 4. Okay, again, sorry, let me clear that. 5, choose 4 is 5. We're multiplying by 2x and multiplying by 3 to the power of 4 here, which is 81. So that's 81y to the power of 4. And then again, 5, choose 5 is just 1. And we get 3 to the power of 5, which is 243. So it will be minus 243y to the power of 5. Okay. So by combining and working out these values and kind of listing out our answer here, I'm just going to write it over I'll probably run over to the side here, but that's okay. So we're going to get 32x to the power of 5. This is just by computing those values. I'm just going to kind of copy it down here to save us working them out. X cubed y squared minus 1080 x squared y cubed plus, let's keep going, over to one side, 800 xy4 minus 243y to the power of 5. So with these binomial expansions, it's very easy, I suppose, to make a mistake, but your mistake might be something very, very small. You might accidentally, as we were saying there, say in this example, minus 3y all squared, you might accidentally just write that down as minus 3y squared instead of squaring the whole thing. And again, it's small mistakes like that that you have to watch out for. The other thing for us to note here as well is just by having a quick look at the equation and the expansion that we end up with, if we look at the powers, we should note that the powers always here add up to 5. Okay, so the total of the powers is always 5, and that is the way it should be as well. And that can help us with kind of quickly computing those values. And that's what I was talking about maybe not having to rely on the theorem and looking at the theorem as much as getting used to the pattern that we're following in computing those values. So we're going to look then at how we might find a specific term. So say we didn't want to just draw out our whole expansion. Say we were asked to compute an expansion to the power of 10 or to the power of 15 or something bigger, then that would take us a considerable amount of time, looking at how long just an expansion to the power of 5 took us to do. So we have a small formula for finding a specific term, and this formula comes from this part at the front of the theorem, and it's also in the middle of the theorem here, generalized in the center. So we have two places where we can kind of remind ourselves of that formula there. Now the good thing I suppose about the first part there is that it reminds us that OR starts at 0. So if we think about that in terms of this expansion, the first term will be when OR is equal to 0. Remember that OR is this number down the bottom here in that bracket. So the second term then would be when OR is equal to 1, and the third term would be when OR is equal to 2. So kind of following that idea on, if we were trying to find T17, then that would tell me that OR must be 16. That OR must be 16 for term 17. And this comes into our general formula here then. So the way I've laid it out is if we want to find term OR plus 1, because remember, if I was looking for the first term, OR would be 0. So OR is always 1 less than the term we're looking for. So if I was looking for term OR plus 1, I would use this general idea on the right hand side, and that's taken exactly from the theorem that we just looked at there. So if I'm looking for a specific term, I just need to remind myself that the value of OR is going to be 1 less than that specific term. And this can help us then to write the general formula for the binomial expansion. And when we have that general formula, we can use that to find specific terms, we can use that to jump to specific values of x, and we can use that quite, it can be quite useful for us, or questions where they maybe give us a coefficient and ask us to find out which term that would be for, and things like that. So in this example here, we're finding the fourth term in this expansion, 2x plus 3, all to the power of 6. So if we write out our general formula for TOR plus 1, it's n choose OR, and it's, I suppose, x in the formula, so we'll stick with that, y to the power of OR. Let's fill in the values that we have here. So we know in this question, n is going to be 6. Let's just get the general form first of all, and then we can try and apply it then for the question here. And I'm just going to take some time here as well, just to kind of go through some smaller little bits. So if we look at the center part here, if we have 2x all to the power of 6 minus OR, we might think, can we split that up a little bit? And we can. So if we had, say, 2x to the power of 3, that would be the same as 2 to the power of 3 and x to the power of 3, which is, of course, 8x cubed. So when we have a number in a bracket, a term in a bracket, to a power, we can actually split that power across the term in the bracket. Okay, so I can rewrite that as 2 to the power of 6 minus OR and x to the power of 6 minus OR. And then here, of course, I have 3 to the power of OR. Now, I can't combine any more of those terms in any way because these numbers down here which we kind of call bases, those numbers aren't the same. So think about as well, if we had x squared by x cubed, I could combine that as x to the power of 5, but here I don't have that. But remembering that what is happening between each of these terms is in fact a multiplication. There is multiplication happening across there. So if we did happen to have maybe 2 to the power of or at the end here instead of a 3, then we could actually simplify this a little bit more. But that's kind of for the next question, I suppose. Let's just focus on where we are. We're looking for the fourth term. So reminding ourselves that for the fourth term, and using this idea here of or plus 1, that must mean that or is going to be equal to 3. So let's fill in this value. 6, choose 3, 2 to the power of 3, x to the power of 3, and 3 to the power of 3. Okay, so working out our value here then, let me see, where's my calculator gone? I would get 6, choose 3, which is 20, times 8, times x, choose 3, x to the power of 3, and 3 to the power of 3 is 27. And working out that value then, multiplying all these values out, I get a value of 4,320 x cubed, and that is my fourth term. And we've saved ourselves the trouble of working out that whole expansion. We could, of course, actually compute that expansion and see where we end up then. If we're asked then, as can happen, and as they do like to ask, to find a term independent of the variable, this is where we're going to be making use of what I was just talking about a little bit before there and looking at the powers of the variable. So it might be x, or in this question it's looking like it's going to be z. If we're going to do that, we need to try and find the value of or which makes the power of the variable 0. Because remember, if the power of the variable is 0, if we have z to the power of 0, that's the same as 1. So that will actually give us a term then that has no 0, that has no z part, or has no variable part in it. So if we look at this example here, the first thing we want to do is set up that general equation the same as before. So n choose or, it's x to the power of n minus or, it's y to the power of or, and we can fill it in then according to the information we have in the question. We know that n is going to be 8. We don't know the value of or, that's kind of what we're looking for. We have 2z cubed here, and it's going to be the power of n minus or, and then in this bracket here I have minus 1 over 3z, and again all to the power of or. So we have a few bits going on here that we need to look at. We have a few little parts to consider. Just as well, when I'm here I will fill that in as an 8 as well, forgetting that we said n was 8 in this question. So the few little things we need to look at here. So we had one part from already. We said that this part here, because it's two things in a bracket, all raised to a power, we can rewrite that by kind of distributing that power across the bracket there. So we'll keep our 8 choose or at the front here, and we can rewrite that as 2 to the power of 8 minus or, and z cubed to the power of 8 minus or. Now to consider this little part, again we have to kind of think back to our indice rules. And one rule that we may have forgotten is if we have something like 1 over x, that is the same as x to the power of 1. If I had 1 over x squared, that would be the same as x to the power of minus 2. And our general rule then is if it's something like 1 over x to the power of a, that is x to the power of minus a. So looking at the question we have here then, if I have 1 over 3z, that's going to be the same as 3z to the power of minus 1 there. It's going to be the same as 3z all to the power of minus 1. Okay, so let's just rewrite that part. We'll not change anything else yet. So it's going to be minus 3z to the power of minus 1 all to the power of or. Okay, so we haven't really changed anything much yet. We could, if we wanted to keep it clear for ourselves, put in a little minus 1 there instead of just having a minus on its own in front of the bracket. But again, that is kind of something we should be aware of. If I have a minus like that in front of that little bracket, that's the same as multiplying it by minus 1. But it might just help us in our next little step. So in the next step, we're just going to continue splitting up those terms as we have done. Now looking at this part here with the z cubed, we should remember from our indice rules that I can rewrite that as z to the power of 24 minus 3 or. So multiplying by 3 there. If we have a power raised to another power, we can multiply those powers. Then distributing across here, I can rewrite this as minus 1 to the power of or, and 3z to the power of minus or. Using that same rule there again, it's already to the power of minus 1, and now we're raising it to the power of or, so we can multiply those two powers. Then if I want to go one step further, then again, just to get everything kind of laid out in the way that I want it, I can rewrite this part over here, so it's minus 1 to the power of or, it's 3 to the power of minus or, and it's z to the power of minus or. So now I kind of have every term laid out, separated in the way that I want it, and the last thing I'm going to do is I'm going to look at these z parts. So as we've said already, if I have x to the power of 3 and then it's multiplied by x squared, that's going to give me x to the power of 5. If I had x to the power of 7 and it was multiplied by x to the power of minus 2, that would give me x to the power of 5 as well by adding the powers. So what I'm going to end up here in total is 2 to the power of 8 minus or, I'm going to use a bracket for this minus 1 to the power of or, 3 to the power of minus or, and z in total to the power of 24 minus 4 or. Okay. So considering then this part here, in this question I was asked to find the term independent of z. And independent tells me that I want z to the power of 0 because I know that that's going to be 1. Okay, I know that that's equal to 1, so that's going to mean that I will have a term where there is no z value. So if we were to take this power here, the 24 minus 4 or, we want to know what value of or do I need to have for that to equal 0. And by doing kind of some simple solving there, we get a value of or equals to 6. So that tells us that when or is equal to 6, my answer is going to have no z part. My answer is going to have no z part. And we can check it obviously fairly easily. We can just sub in 6 into that general term. So I get 2 to the power of 2, I get minus 1 squared, I get 3 to the power of minus 2, I get z to the power of 0. And by solving all of that out, I'm going to get a value of 112 over 729. Now, if we weren't happy with subbing it into that point, we could easily go back and sub it into the very, very, very original equation, and that would be fine also, and we would still get out the same answer. What's important for us, I suppose, with this example here specifically as well, is it can help us if we're asked to find any particular power of z. So if we were asked to find what term would have z to the power of 1, we would take this part here and we might put it equal to 1. Or equally, if we were asked to find where z is equal to the power of 2, we could set that equal to 2. Okay, if we're asked to find the coefficient of x squared, well, that tells us, well, I need the power of z to be 2. Okay, so using that as appropriately as we can. The key thing as well, I suppose, and the part that can cause issue would maybe be this part here, where we're kind of rearranging that 3z to the power of a minus number. And a lot of that can get very, very easily confusing. So it's just about, I suppose, keeping it as straight in our heads as we can. And that is probably one of the harder elements of this question, really, is that rearranging segment there. So let's just look at some of these practice questions then. So we have a practice question that is just on expanding completely using the binomial theorem. So let's just maybe quickly run through this one. We'll maybe not spend too long on it. So again, it's to the power of 6. So I would start by doing 6 choose 0. My first term is 4x, and we know from using the theorem that that's going to be to the power of 6. I then move on to my second term, which is 6 choose 1. 4x, those powers are going to go down, and the powers of 6y are going to start going up. So that's to the power of 1. Then 6 choose 2, I'm going to get 4x to the power of 4. I'm going to get minus 6y to the power of 2. 6 choose 3, I'm going to get 4x to the power of 3 minus 6y to the power of 3 also. And again, as we've noted already, these powers adding up to 6 here at all times. 4x squared minus 6y to the power of 4, 6 choose 5, 4x multiplied by minus 6y to the power of 5, and 6 choose 6, and it's just minus 6y all to the power of 6. So laying that out there, the powers of the first part of our expression going down, the powers of the second part going up the way, and keeping our 6 choose 0, 6 choose 1, 6 choose 2, and so on and so forth, keeping that kind of in the center the entire time. Okay, still doing those calculations out as best as we can. So let's just, I suppose, work out these values. Where's my calculator gone? It is here. Okay, so 6 choose 0 gives me a value of 1. 4 to the power of 6 is going to be 4096. 6, okay, 6 choose 1 is going to give me 6. 4 to the power of 5 is going to give me 1024 x to the power of 5, and that's going to be my minus 6y. 6 choose 2 is 15. 4 to the power of 4 is 256 x to the power of 4, and then my minus 6y squared is of course 36y squared. Then 6 choose 3 will give me 20 by 4 to the power of 3 is 64 x cubed, and 6 cubed is 216, so 216 y cubed, and that's obviously going to be negative as well because we haven't changed, because we're doing it to the power of 3 there. Then 6 choose 4 is 15, 4x squared is 16x squared, and my 6 to the power of 4 gives me 1296 y to the power of 4. And again, a lot of this just becomes kind of tedious and long, rather than being, I suppose, particularly difficult in and of itself. Of course, there are difficulties in making sure that you're able to do it in the first place. But once we kind of have got a grasp of it, it is just kind of tedious and easy to make a kind of silly mistake on. So it's just making sure, I suppose, that we don't let ourselves do that. Okay, so again, I suppose same as the last time, I'm maybe just going to take then our answer for the last little step here. So we get 4096 x to the power of 6. By multiplying these terms here, that is going to give me an overall answer of minus 36864 x to the power of 5y, and then plus 138240 x to the power of 4y squared, then a minus 276,480 x cubed y cubed plus 311,040 x squared y to the power of 4 minus 186,624 x y 5 plus 46656 y to the power of 6. What I will say about the binomial expansions is you are much more likely to get a question looking for a general term than you would be in your leaving cert to get a question doing a full expansion, because there is a point where they are not really testing you on anything particularly except general algebra and multiplying out. So I would say there definitely is more to be said for these general term ideas. That's not to rule out them completely giving you an expansion to do, but sometimes they might just be of smaller value, and it comes up in some other topics as well, so they can kind of test it in that way. So let's just quickly run through some of these other exam questions, I suppose. So this is the exam question from 2012, the SEC question, and we're asked to find an expression for the general term. So this is what we were doing in the previous section. So that's our one with t or plus 1. In this question, it's to the power of 10. So we'll say 10 choose or. It's 3x squared to the power of 10 minus or, and it is 1 over 2x to the power of 4. Okay. If we're looking for the general term, what we'll try and do is simplify this down as much as we can. So using what we learned and what we explained in the previous example, I can rewrite this as 3 to the power of 10 minus 4. I can rewrite this as x to the power of 20 minus 2or, so that's multiplying by that power of 2, and I can rewrite this part as 2x to the power of minus or. Okay, I know I'm jumping some steps here as well, but kind of if you're following along and you've followed the previous example as well, you kind of see where we're going with this. So we get 2 to the power of minus or and x to the power of minus or. And lastly, I'm just going to look at combining my x parts there. So I get 10 choose or, I get 3 to the power of 10 minus or, I get 2 to the power of minus or, and I get a total of x to the power of 20 minus 3 or. Now, for part 2, we are asked to find the coefficient of x to the power of or. So what we've done now is we have laid our general term out in such a way that we see the exact total power of x. By combining the different x parts, we can get the total power of x for any term in this expansion. So by looking at our total term here, that is 20 minus 3 or, and we want that to have a value of 8 for this particular one that we're looking at. They want that x to be to a power of 8. So kind of solving that, then we get 12 is equal to 3 or, which tells me that or is equal to 4. So knowing that or is equal to 4, I can then sub that into my general term. I get 10 choose 4. We can either sub it in at the end here, or we could sub it back in at the top. Maybe since we subbed it in at the end the last time, we might sub it back in at the top this time and work it out fully, just to show that we should get the same answer. So I get 6 here, and I get 1 over 2x to the power of 4 here. Looking at my calculator then, 10 choose 4 is 210. Then 3 to the power of 6 is 729. And that's x to the power of 12. And then here we have 1 over 2 to the power of 4 is, of course, 16. Okay. Oh god, everything's gone. 1 over, let's try again, 16x to the power of 4. And then by doing some simple algebra, if we have an x to the power of 12 on the top, divided by x to the power of 4, and simplifying and kind of bringing everything together as best I can, that's going to give me an answer of, let me see, 210 by 729 divided by 16. Sorry, let me just divide my answer by 16 there, and that gives me an answer of 76,545 over 8 x to the power of 8, which means that if we just want to exactly answer this question, let's just lay out that means that the coefficient is 76,545 over 8. Okay, again, just making crystal clear that we have answered the question being asked of us there. Looking at part 3 then, part 3 says, show that there is no term independent of x. So looking at our general term here, if we wanted the term to be independent of x, we would be looking at our power of 20 minus 3 or, so let's have a look there, and we would want that to be equal to 0. If we kind of move things over, that gives me 20 equals 3 or, and that gives me that or is equal to 20 over 3. And we should know, or we may not have dwelled on it too much there, but we've kind of seen from what we were looking at and the fact that or is always that number at the bottom of our choose function, or has to be a kind of natural whole number. Okay, or has to be a whole number. And in fact, or is always kind of one of our counting numbers, so 0, 1, 2, 3, 4, and so on and so forth. So because it's not a whole number, that tells us there is no term independent of x. Okay, we're nearly there. I know that this video is kind of running on a little bit, but we're nearly there. We'll do one more example because I know these general term and term independent ones, they can be the ones that people find really, really tricky. So it's just kind of getting it laid out enough and just getting the practice of them. And obviously we'll have our solutions for these ones for you to practice, so you can kind of stop the video before you do it if you want to. But let's find the general term for this one. So again, t or plus 1 is going to be 9, choose or, 2x to the power of 9 minus or, minus 1 over x squared to the power of or. So let's have a look now at trying to simplify this down. So here we can rewrite the 2 as 2 to the power of 9 minus or x to the power of 9 minus or. And trying to rewrite this middle part, let's maybe take it in 2 steps, I suppose. So we'll write minus x to the power of minus 2 all to the power of or. So remembering that 1 over x squared is the same as x to the power of minus 2 and keeping that minus in front then. And now we're going to kind of separate that out. 2 to the power of 9 minus or x to the power of 9 minus or minus 1 to the power of or and x to the power of minus 2 or. Okay, following through then with that and kind of combining our x terms as we've been doing with the previous questions, I get 2 to the power of 9 minus or, I get minus 1 to the power of or, and I get a total of x to the power of 9 minus 3 or this time. That's my general term now. And we can say the general term here, this technically is our general term, but we are always best to try and simplify it down and combine our x values and all to give us a really, really condensed general form for the question. So then looking at part 2, again, we're finding the value of the term independent of x. So independent of x tells me that I want to have x being equal to 0. So that means that the power of x here, the 9 minus 3 or, must be equal to 0. So that means that 9 is equal to 3 or, which means that or must be equal to 3. And if we want to find now the value of that term, we can remind ourselves that that's going to be term 4. And I'm looking at 9, choose 3, and I'm going to just sub into this n part here. So 2 to the power of 6 minus 1 to the power of 3, x to the power of 0. 9, choose 3 is 84. 2 to the power of 6 is 64. And minus 1 to the power of 3 is going to be minus 1, so I'm going to get a negative answer. 84 by 64 minus 5,376 as my answer to that there. Okay, so we've looked at a fair bit there, and I know this video has run on a little bit, but definitely skip through and pick to the parts that are most pressing for you. So obviously with binomial we need to be able to do the general expansion. We should be able to get a general term and jump to specific terms in the expansion, and then the idea of getting a term independent of x. I suppose technically if we are asked for the general term, we can use that general formula, sub in and kind of leave it in that form, but it's always worthwhile going further because the general term questions will typically require you then to look at powers of x and things like that. So it's always worth pushing that little bit further on. We can see there as well with our binomial, it's really important that you are crystal clear on your powers and your rules of indices as well. But yeah, absolutely. So keep the practice of these questions and that general term and the expansions in general, and you'll be good to go.